Yo, it's Miss Johnson with your first math video of Math 2. All right, y'all, I just found my tablet, so sorry for the delay. You can see there's a bunch of boxes in the background. Still waiting to be unpacked, but we'll get there when we get there. Um, yeah, so I'll make these for every review. I think I'll post them before the test next time, now that I'm thinking about it, right? If there are other topics in class that you want me to make a video for, let me know, either in class or over email. I know this is a really good resource during the pandemic, and it's one of the things that we can just keep going if we really want it. All right, let's get into it. This is my high tech setup. It's just Microsoft Paint. I've posted everything from the review in Microsoft Paint. I'm just going to talk about it. Feel free to only do the sections you want to do, only listen to the sections you need to do, and feel free to email me any questions if you've got them, right? All right. Okay, let's read the directions. These don't matter. All right. Identify the pattern as exponential, linear, or quadratic, or some other kind. Indicate through your work how you can tell. Identify the pattern of growth as constant, exponential, or linear. If it's other, you don't have to do the other parts. And then we'll also do a secondary model on each of these, just like in the test. Okay, so A and B are tables. Whenever we have a table, the way we're going to see what type of function it is looking at the first and second differences, or if it's multiplication, the ratios. So here, we can tell that it's not all the same multiplication, because this would be times 1 and this would be times 0, so already we're toast. So let's see the first difference. Oh my god, my handwriting's worse online. First difference. This is minus 6. Going from 0 to 4 is negative 4. Negative 4 to negative 6 is negative 2. Negative 6 to itself is 0. That was kind of a weird one. And then negative 4 back up to negative 6 back up to negative 4 is actually positive 2, which is also a little wacky. These are not the same numbers. You might have noticed. So we'll look at the second difference. Negative 6 to negative 4 is positive 2. And then we go up again 2 to get to negative 2. Up again 2 to get to 0. And then plus 2 again to get to positive 2. The second difference being constant, so these numbers being the same, even though these numbers aren't, means our pattern is quadratic, right? Our function is a quadratic function. So when we're looking at the pattern of function for all the first part, this is when we actually have to do some computation, right? And then the pattern of growth is always directly from the function. Quadratics always grow linear. Anytime you write the function is quadratic, it's always linear growth, right? It's kind of like the definition of quadratic. So when we write linear, it's not really a computation. We're not doing math. We're interpreting math. Cool. The secondary model, we don't know how to make equations for quadratic functions yet. That's something we'll learn in later modules. So we are going to use a graph for the secondary model here. Let me get this going on. Nope. Boom, boom. I understand now. Our leftmost point is negative 3 and our rightmost point is 2. So I'm going to put those in there. We got to go up 6, negative 6 as well. 1, 2, 3, 4, 5, 6. And then we graph the table by treating the xy rows as coordinates. So negative 3 up 6, negative 2 to 0, negative 1 to negative 4. These are both negative 6, and then this one comes back up to negative 4. We can connect these if we really want to. All right, let's do it again. Run it back. To be honest, I think the one on the test was quadratic, but let's do the exponential one anyways. Here, we can see if they're adding or see if they're multiplying. Here is multiplied by 2, the 3 to 6, the 6 to 12, the 12 to 24, and the 24 to 48. So we can check the 3 halves times what equals 3. It turns out that it's times 2, right? So this is also times 2. Whenever the first ratio is constant, ratio is constant. That means the pattern's exponential. Nice. Again, for the growth, anytime we see exponential, we immediately get to say that the growth is exponential. Nice. The secondary model here could be a graph, or it could be an equation. Boom, boom. For the graph, we do what we did for the other table, which is we put little tick marks, 10, 20, 30, 40, 50, 60, and then we make it go up to 50. And we kind of eyeball it, right? 10 is very close to the bottom. 20 is pretty close. This is pretty close. This one gets bigger. This one gets bigger. This one gets bigger. Then again, we can connect the dots if we want to. The equation, and I'll move it down to equation eventually. The exponential equations always look like y equals a times b to the power x, where a is your y-intercept, so your starting point when x equals 0, and your b is your ratio. It's the thing you're multiplying by each time. Also, when your x's aren't just 1, 2, 3, 4, and 5, you kind of have to account for that. Here, because we're counting by tens, we divide by 10 up in the top. Our ratio here, so for our actual equation, our ratio here is 2. We're counting by tens. And to figure out this, instead of going down by multiplying by 2, we're going to go back up and divide by 2 and get that at x equals 0, our y is 3/4, so that becomes our a in our equation. That's the table one. Again, this video is going to be pretty long, so just skip to the part that you actually need. All right. The pattern here is linear. How do you know, Miss Johnson? It looks like a straight line. Linear equations always grow constantly. So it's always a constant pattern of growth, a constant rate of growth. The secondary model, we can make a table, x and y, and simply just put the x and y coordinates of a couple points, right? This one is 0, 4. This one is 1, 2. This one's 2, 0. This one is -1, 6, right? So we can just port these into our table. Or we can make an equation. Let me actually transparent selection freeform. There we go. That's probably fine. It's not fine. That's definitely fine. Nice. Okay, and then the equation the equation for linear functions always looks like y equals mx plus b, where m is our slope and b is our y-intercept, right? Here, our y-intercept is 4, because that's where it hits the y-axis, and our slope is -2. And this is because we're, let's do it like this. We're going down 2 and over 1 to get from point to point, and -2 divided by 1 is -2. So here our equation would be -2x plus 4. Either this or the table works for our secondary model. All right, let's run it back. Here, to be honest, this one, if we connected the dots, it looks exponential, but if we kept going on this side, it could look quadratic. So we don't want to do this one just by shape alone. We actually want to use the table and figure out what's going on. Here we've got -1, 1, 0, 3, and 1, 9. This one's -2, something. It's kind of like in between. It's a fraction. So we want to do a little more research before we make a decision on what it actually is. So let's write these down. So -2, we don't know yet. This one's 1, this one's 3, this one's 9. Here, both of these are times 3. So now we're thinking, oh, it's probably exponential, right? If we divided by 3 to figure out exactly what this one's going to look like, it's going to be 1/3. We'll say that this is exponential. Exponentials immediately grow exponentially. Nice. And we've already made our secondary model while we were figuring out what type of growth this was, or what type of pattern this is. The secondary model also could be an equation. Boom. And here we'd say it's our y-intercept times our ratio to the power of x. Right? So we're starting at 3 and multiplying by 3 every time. All right, next version. We've got like the actual equation, not just the discrete function. Pattern of function, this looks like an upside down U, so it's definitely quadratic. Quadratics always grow linearly. We don't know how to do these equations yet, so we're going to make a table. This is my table button. And then this one, the way I'm going to make a table for these is I'm just going to find points that are actually on the grid, right? And then just write them down. So this is 0, 1, 2, 3, and 4. This is 0, 0, 1, 3, 2, 4, 3, 3, and 4, 0. My housemate's coming in. And again, we don't know these equations yet, but if we really wanted to, we would notice that this is like a regular parabola flipped upside down, moved over 2 and up 4. So we'd say flipped upside down, over 2, and up 4. For those who are curious. We'll get there eventually. All right, another one. I'm hip 10 years ago, I promise. So we're going to find the points that are actually on the grid. We're going to say that looks like a straight line. It's linear. Linear functions grow constantly. Oh my goodness. Don't do that. Oh, I wish. Okay, nice. Easy. And then the secondary model, we can either make a table, which I'll do now. Boom, boom. Where this is -3, 1, 0, 2, or 3, 3, and 3, 3. Nice. Or we can make an equation where we say this is up 1 over 3. So our slope is 1/3 plus 2, since that's our y-intercept. Seems pretty good. And now for the ones that everybody loves the most, equations. This equation, part H, looks like y equals mx plus b to me. Right, we've got a number, an x, and then another number, which means that this is linear. The pattern of linear growth is always constant. That's not how you spell constant. Then the secondary model is a little bit weirder for equations. We can make a table. And the way you make a table for an equation is you just pick a couple x's and then plug them into the equation to get your y's. So the way we'd find this one is we'd say it's rewrite the equation, but plug in -1 for every x. So 5 times -1 is -5, minus 2 is -7. We could plug in 0 and get -2. We could plug in +1 and get 3. We could plug in 2 and get 8. That's a perfectly reasonable table. Or we could graph it, again, by making the table and plotting those points. Or maybe even a little bit better. Brushes, this 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, Cool. We can start at -2 on the y-axis, because that's our y-intercept. And then we can do the slope 5. So we go up 5 over 1, down 5 to the left 1, and then we can just draw a line that goes through these points. I didn't really like tables. That's my feeling. I'm not an artist. I'm not super good at making graphs all the time. So I generally go with tables, but you'll find the thing you like best. Okay, here for part G, when we look at the pattern of this function, it sort of looks like a times b to the power x, because there's an x in the exponent. The exponent. So that's an exponential function. And then again, exponential, right? And then the pattern of growth is exponential. Cool. Secondary model. We can do a table. We can do a graph. The table is my favorite, so we'll do it first. X, Y. We'll plug in some random numbers. Usually I plug them in around 0, though, because that's like where graphs usually happen in school. So here we do 5 times 4 to the power 0. Here we do 5 times 4 to the power 1. Here this one's 5 times 4 squared. And this one's 5 times 4 cubed. 4 to the power of 0 is 1. Anything to the power of 0 is 1. So this is 5. This is 20. Because that's what I actually write. 4 to the power 1 is 4. 4 squared is 16. And then 4 cubed is 64. This is times 4, right? This is something you can use a calculator for, or it's something you can say, once we read this, this says start at 5 and multiply by 4 to get to the next one. Oh, we do. This says start at 5 and multiply by 4 each time. So we could have started at 5 and then said times 4 times 4 times 4 and done none of this stuff. Okay, I'm going to pause the video there, post this one, and then do the next couple in a different video, just so people know where they're going. How do I stop it? Impossible to say.